Hello everyone, welcome to Bodo's Wide Band Gap event for 2022. We're going to talk today about Qorvo's SiC FET technology and what it does for next generation onboard chargers. My name is Anup Bhalla, I'm the Chief Engineer for Power Devices at Qorvo. Before I launch into this discussion, I'd like to pay my respects to John Palmer, who passed away recently. John, I think you all know him, was the pioneer in the world of silicon carbide. And without him, I really don't think this field would be where it is today. So he will be missed and remembered. We have been working on our Gen 4 technology for several years and expanding the offering of products we have in various package types, both through hole and an increasing number of surface mount options. So this chart shows some of the released products in TO-247 and the D2PAK-7 lead, or the TO-263 7 lead package. All of these use the cascode architecture to build the SiC FET, and the core JFET technology, it has the lowest on resistance per unit area that you can get in silicon carbide today. It offers, because of the small chip sizes of the JFET, you get low capacitances, so that allows you to get good figures of merit. The silicon FET that we use as the interface device has a 5-volt threshold, and it allows you to drive simply from 0 to 12 volts or 0 to 15 volts. And that makes the gate drive of these devices compatible with silicon MOSFETs, IGBTs, and silicon carbide MOSFETs. So you can use any of these gate drive methods. It gives you a nice low forward drop third quadrant diode with nice QRR. And because the chips are so small, we've been using sintering in our discrete packages for a long time now, even with the previous generation. And this is necessary to get the heat out of the die. So this gives you superior thermal performance and removes the solder joint as a mode of failure for power cycling. And this technology is available both in surface mount and through hole. So we're going to take a look at what all this does for next generation onboard chargers. Technology is constantly evolving, and it's the same with silicon carbide FETs. The Generation 4 JFET technology has come a long way in optimizing the trench structure, reducing drift and substrate resistance. And the blue dots on the right-hand chart show that it's getting within sight of the 1D limit of silicon carbide for unipolar devices. And you can see that the resistance per unit area in the 750 to 1200 volt class is well below that of silicon carbide MOSFETs, GaN devices, as well as silicon superjunction devices. And the point of talking about RDSA is that if you can offer a low resistance in a given chip size, it means you can pack a low resistance into a small package, and this can be very useful in cutting losses in a wide range of applications. So this picture is looking at the 750 volt class of devices in the D2PAK-7 lead, and Qorvo offers a 9 milliohm device that is well below the competitive offerings based on silicon carbide MOSFETs. And when the chips become small, their capacitances directly become lower. And once that happens, you not only get a low RDS on per unit area, which is the subject of the leftmost chart, showing that silicon carbide JFET based FETs have the best RDS on per unit area, but then the lower capacitance leads to improved figures of merits for hard switching, which we capture through RON EOSS, and soft switching, which we capture through RON times the output capacitance. And in particularly for soft switching, the other thing that's beneficial is you can save on high frequency gate drive losses by just simply using a lower swing on the gate voltage while having zero impact on RDS on. So you can just run the gate from 0 to 10 volts and save on gate drive losses. When the body diode turns on, it only has a 1.5 volt drop, not a 3 volt drop like a silicon carbide MOSFET. So those losses can also be improved upon. We're going to talk about both through hole and surface mount devices and how you can use them for onboard chargers. So a little introduction to the surface mount version would be in order. So the D2PAK-7 lead package from Qorvo, it's a unified package that we use across the board from 750 volts to 1700 volts. And so it's the high creepage version. And you can see from the table at the bottom that without compromising the creepage and the clearance, which are basically what's used for 1700 volt devices, the sintering technology allows us, even with our small chips, to get very good thermal resistances. So that's a comparative number there for our 9 milliohm device versus the competitive silicon carbide MOSFET devices. When we set out to build an onboard charger, we have choices between a through-hole based implementation, which is traditional and much easy, and the heat sinking methods are well understood, and we could use a surface mount version, and in this instance we'll explore the IMS implementation with surface mount devices. So the range of devices we are considering is shown in the table here. We have a wide range of RDS-ons in both the TO-247-4 lead and the D2PAK-7 lead. The D2PAK-7 lead can't really fit the 6 milliohm device, but all the other devices from 9 to 60 milliohms are available in both packages. And you can see with the table on the right that the TO-247 has a much larger die pad area, so generally is able to, you can remove more heat compared to the D2PAK-7 lead, but the inductance in the D2PAK-7 lead is a lot better. The creepage and clearance also is superior for the D2PAK-7 lead option. In onboard chargers, liquid cooling is generally available. So let's look at how one might mount the through-hole device, the TO-247-4 lead, or the surface mount device, D2PAK-7 lead, if you have that environment. So on the top, we see that the TO-247-4 lead is mounted to the PCB. It is separated from the aluminum heatsink by a piece of ceramic with thermal grease on both sides. So this ceramic piece is not a DBC, it's just a piece of ceramic. There's no copper on either side. On the bottom, so it's just an isolator. And on the bottom, the D2PAK-7 lead is mounted on an IMS substrate. It has a dielectric layer of between 150 and 300 microns thickness. The topside copper is 300 micron, and then the cooling aluminum, the bottom aluminum is directly liquid cooled and is 3 millimeters thick. So once we calculate the power losses in these devices to get the temperature rise, we'll need to know the thermal resistance. So now that we have context for the thermal stack-up, we can use simulations to work out for the range of die sizes what the thermal resistance will be from junction to the fluid in both of these scenarios, the through-hole or the surface mount. And so we've done a range of simulations to sort of get some boundary conditions for this, from small die, the 44 milliohm small die in this case, to the 18 milliohm somewhat larger die. And we can separate out the thermal resistance junction to case and from the case to the fluid. And so for the sake of this analysis, we can use 0.6 degrees C per watt from case to fluid for the TO-247 with this large die pad, and 1.2 degrees C per watt for the D2PAK-7 lead, case to fluid, when it's mounted on an IMS substrate. Qorvo offers a very easy to use online tool called the fetchet calculator, which has the models for all the parts built in, equations to allow you to calculate the switching and conduction losses based on circuit topology. And so using that calculator, once you input all the input conditions shown on the left-hand column, the calculator immediately outputs the efficiency you can expect, the losses in each of the switches, breaks the losses out into turn on and turn off losses, and estimates the junction temperature rise. And the RDS-on is, of course, also automatically calibrated to reflect the RDS-on at that temperature. So that is done self-consistently. And you can then go through a selection of different switches to see what the outcome and power losses will be. The right-hand column shows a typical output, and the table at the bottom shows the optimum usage conditions for each device. So armed with that information, we can now take all of these different parts and do some case studies on them. So this first one is for a 6.6 kilowatt totem pole PFC for an onboard charger. So we can build that with the TO-247 devices shown on the right-hand side table with the light blue lines, and the green lines reflect doing the same thing in a surface mount option with the somewhat worse thermal resistance but better inductance and better switching losses. So you can see that from an efficiency point of view, from a junction temperature peak point of view, there's a wide range of options that can work in this case, all the way from the 18 milliohm device to the 60 milliohm device. And based on cost and total dissipation considerations, the user has a wide range of options, and it's also clear that both options work well, the TO-247 option and the surface mount option. So, users can really just decide based on what they're trying to achieve, which of these options they want to go with. And then here is another exercise for the CLLC stage if it was using a 750 volt device and was only for 400 volt bus. The same sort of table is on the right. It's a 6.6 kilowatt CLLC working at 300 kilohertz. And if we look at the losses for the TO-247 version and the B7S versions, the loss numbers are very low. The temperature rises are very small. Again, both surface mount options work, through-hole options work. Even the 60 milliohm device is able to do the job here. And you can utilize all the benefits of the device in low gate charge. Use a 10 volt gate drive if you want. Utilize the low body diode drop and even increase the frequency further if that's desired. And this chart is on the 1200 volt Gen 4 family. These devices are optimized for use in onboard chargers. We are showing a picture here of the through-hole options with the surface mount options in D2PAK-7 lead coming soon. So here is a worked example using the same thermal stack up and the fetchet calculator to work out what could be done with these devices in this example, the active three-phase front end for an 11 kilowatt class onboard charger. And the table below compares the performance you would get using a generation 3 device in the left-hand column with the generation 4 device on the right-hand column. So here, the 30 milliohm Gen 4 device has a smaller die size than the 40 milliohm Gen 3, but it gives you lower losses because of better switching, higher efficiency, less power loss per phase, and basically, on account of lower losses, it runs cooler, even though the die size is smaller. And a final example, using the 1200 volt devices for the DC to DC portion of the 11 kilowatt OBC. So power losses are excellent both for Gen 3 and Gen 4. In Gen 4, for the same sort of die size, we would have lower RDS on. That would lead to lower losses per FET, as shown in the table between the Gen 3 and the Gen 4. So higher efficiency, less losses per phase, and it would therefore run cooler. So we can quickly summarize now that there's a wide range of Generation 4 based SMT devices and through-hole devices, really opening up a great deal of choice for people designing onboard chargers to get higher performance levels, more cost-effective options, less heat dissipation, and these discretes can be used everywhere from 3.3 kilowatts, in fact, up to 22 kilowatts. So especially in the 6.6 to 22 kilowatt range, these are great solutions. Thank you for listening, and I'd be happy to take your questions.